Okay, so acid-base buffer solutions are any solution that contain both a weak acid and the conjugate base simultaneously. They have to contain both, and it has to be weak, can't be a strong acid. The example, which came straight from the previous video, was acetic acid and its conjugate base acetate. And the unique property of acid-base buffer solutions are that they can resist changes in pH, and that's because you have both of these species, the acid and the base, present in the solution at the same time. And that's where the origin of the word buffer comes from, because as you add acid or base to that solution, it resists, or it's buffered against a significant pH change. Where these are common are virtually all biological systems. And the example is that you could eat a lemon or drink orange juice in the morning, and the pH of your body isn't going to swing wildly to pH 2 and cause you to die. And that's because you have many, many buffer systems in your body that can resist reasonable additions of acids or bases and maintain normal homeostatic pH levels. So in the case of acetic acid and acetate, if we were to add some strong acid in the form of H+, it would go and react with the weak base, the acetate that's present, and neutralize it. Similarly, if we were to add strong base in the form of OH-, it would react with the weak acid and buffer that. And so depending on the concentrations of these two things, how much we have in solution, that defines what we call the buffer capacity. How much of each of these acids and bases can we add and still resist a pH change? So we'll talk about buffer capacity as we move through these videos. So let's jump right into an example of what happens when you add a strong acid like H plus or OH- strong base to a buffered solution. So we have an initial condition. So our beaker contains, it's 1 liter in volume, and it has the same concentration, 0.1 molar of acetic acid and sodium acetate. Remember, sodium acetate is the same as acetate because this is just a salt that dissociates. Sodium is just the carrier of this ion because you can't have a bottle of ions. You have to have it in a solid salt form. And the perturbation to this system is that we're going to add 0.01 moles of solid chunk of sodium hydroxide, and we're going to see what happens to this system. So I really like to sketch these problems out because it helps me understand what's really happening in the system. And it's not a sophisticated sketch, it's just a beaker, and it tells me I've got a liter, and it tells me what I have in the system, and I'm just using the abbreviations here for weak acid and conjugate as HA and A-. It's the same that we have here, and I know that the addition of the hydroxide is the perturbation that we are evaluating. Okay, so what we know is happening during this perturbation step when we're adding hydroxide is that we have an acid and it's going to react with the base. And this comes straight out of the discussion a few videos ago about neutralization. This is a neutralization reaction, right? We have acetic acid, the weak acid, plus strong base is going to make acetate and water. And we can draft up an ice table because we have some initial conditions and we have a change now. But the change, rather than just something being allowed to reach equilibrium on its own, we're actually adding something as the change. And so we can use the ice table in the same way. So our initial condition looks like this. And by initial condition, I mean the moment we add the hydroxide, the perturbation to the system. Because we add it to the system, we know a reaction is going to occur, but the initial condition is the moment just before that reaction starts. So that's time 0. And that's why I include both the HA, the acetic acid, at 0.1, but also hydroxide at this should be 0.0. We also then have 0.1 of the acetate, and water is, it's not 0, but it's negligible. It doesn't matter in this case. And so the change is going to be what happens after that time 0, after these things are allowed to react. We've already determined that a weak acid and a strong base have very large neutralization equilibrium constants, or Kn. So we know this is going to proceed stoichiometrically. And so what's going to happen is this hydroxide is going to react with the weak acid, and it's going to produce equivalent amounts of the CH3COO minus. And so the change here would be that this amount of hydroxide, that 0.01, all of that's going to react because this has such a large equilibrium constant. So all of that's going to get destroyed. And in doing so, the hydroxide is grabbing this proton, which means it's reacting with and destroying that molecule HA. So that means the same amount of that is going to be destroyed. And we can say the same amount, 0.01, is going to be created for the acetate, because for every 1 mole of the acetic acid we destroy, we create 1 mole of the acetate. And so that means at equilibrium, we're going to have 0.09 here, we're going to have 0, we're going to have, in this case, 0.11, and then the water, of course, is not consequential. Okay, so now it's important to know or ask ourselves, at equilibrium, what do we have in the system? Well, we've gotten rid of all of the strong base, that's gone. And so what we really have is the weak acid, its conjugate base, and we, of course, have water. And so we can think about, well, what would happen in that system? Well, both of those things, a weak acid and a weak base, can react with water. So the actual equilibrium that can proceed here, now, in this system, is going to be the weak acid reaction with water. So we can write this out as the CH3COOH plus water that will dissociate into H3O plus and the acetate ion. Remember, the reason I can write this now is because there's nothing else in the system except for those things that can react with water. That's at equilibrium. That's different than the first reaction, which had the hydroxide present. But once that all got neutralized and left over, now we are shifting the reactions that can take place. Okay, so we have the reaction. We know what Ka is. We've used this a million times. We can look it up. It's 1.8 times 10 to the minus 5 for this reaction. So I can write up the equilibrium expression, and I can substitute in the known quantities because we know that the system is now at equilibrium, and we're just trying to figure out what the pH of the system is. So we don't know hydronium ion, but we do know the acetate and the acetic acid and Ka, so we can solve for hydronium ion. If we solve for that value, we get something like 1.5 times 10 to the minus 5. Negative log of that gives us a pH of 4.82. Well, what was the point of this whole exercise? Well, remember, we're talking about a buffered system, and we defined a buffer as something that can resist changes in pH when you add acids or bases to them. And so we started out with equal amounts of the acid and the base. And then we added this perturbation, which was pure hydroxide. And if we were to look at this equilibrium expression in the end, right, if we just had these original amounts and we didn't have the perturbation, we could input those values directly for these two numbers. And so those values would be 0.1 and 0.1. And if those are true, at 0.1 and 0.1, they'd cancel, and our hydronium concentration would simply be 1.8 times 10 to the minus 5. But when we added the base, it shifted those away from 0.1 and made them 0.11 and 0.09 respectively, which made our hydrogen ion concentration shifted from 1.8 times 10 to the minus 5 to 1.5 times 10 to the minus 5. And so in reality, the pH changed very minusculely simply because we barely perturbed that ratio of things. Think about if we didn't have any of the weak acid present and all we had was the acetate ion. In that case, when we added hydroxide, we would end up having lots of base in the solution, and we'd end up with a pH that would be probably in excess of 10. So let's quickly look at that scenario just as a comparison. So in summary, what we had is this buffered solution where we had equal parts of the acid and its conjugate base. If we just computed the actual concentration of hydronium ion and its corresponding pH, that'd be about 4.74. And then we added a bunch of strong base and it shifted only to 4.84. So there was this resistance to pH change upon addition to hydroxide. So let's think about just a pure water solution, so no buffer. We know that would have a pH of 7 because of the dissociation of water. So we could just write up pH is equal to 7 to start with. Now, upon the same addition of hydroxide, what would the corresponding pH be? So this one we can solve really simply just using Kw, because we know how much hydroxide we're adding to the system, and we know what Kw is. So I can just take Kw divided by 0.01, which is the concentration of hydroxide. That gives me H+. That gives me a pH, if I take the negative log of that, of 12. And so you can see the consequence here. So when we have no buffer, our initial pH is 7. And when we add the same amount of base that we did to our buffered solution, we had an increase in 5 pH units. But if we compare that to our buffered system with just a weak acetic acid and acetate ion, we add the same amount of strong base and we get a 0.1 unit change in the overall pH. So that's the power of a buffer. And this is why biological systems are so robust to change, is because buffers essentially neutralize any addition of strong acids and bases within reason, within whatever the buffering capacity of that system is.